So in the previous lectures we have discussed on various topics, right, of neural networks. What is neuron, how does it work, what is perceptron, what is ANN, CNN, LSTM, everything. We have also implemented sample use cases with respect to that. Here we are trying to understand this hype word called BERT. You might have all heard of BERT to a certain extent, right? So what is what is its importance? What are BERT transformers? What is BERT embedding? Now compared to any word embedding or word to X. So we already know about word to X, word to X, globe word to X, and normal word to X, right? So what is it reference of embedding? What are these transformers? Obviously, we all know that they are used in very nice applications like neural machine translation, text classifications, or text summarizations, and all, right? Even LSTM, in one case, we have actually seen that it's good to work with NLP tasks. Yeah, but what is BERT then, right? So basically, even though we go with LSTMs are not still proper to a certain extent. There are actually better ones. Okay, so LSTM also has problems. See, that's when the progression happens from one model to another model, one architecture to another model, where you find the loops and you want to make it better and better. So LSTM, in one way, if I say, it has also problems. LSTM, firstly, it is slow. So if you see LSTM, actually it is slow. And secondly, it is not truly bidirectional. It is not truly bidirectional. So even though there is a concept called bi-LSTM, okay, where it learns from left to right and right to left of a particular paragraph or sentence and try to understand the context, but still it is not proper. So when it is going from left to right and right to left, it is trying to connect those words. I mean, it is actually trying to connect those words, and it's actually missing out the real true context. It's not happening properly in good understanding. Suppose if I say, what happens is, if I say I'm eating an apple, okay, and there's another word called apple has released a new iPhone, okay. So in this apple, the words are same but the context is different. But if they come in a particular sentence, I am eating an apple and watching my Apple phone, so it misses the context. It is going from left to right and right to left, and based on certain words it's trying to miss the context, okay. So it is not very ideally good at understanding, okay. It is not, as per the market scenario, it's not so good at understanding. It can understand better, okay. So that is why people, these transformers of like BERT have come into picture, okay, which are already having a lot of good embeddings in it, okay. So what are transformers? Transformers are very fast. Why? Because they are already having pre-trained models and they are already fully connected layers which are there. We just need to work with the output layers. Layers, that's all. Already 90% job is done. That's why they are very fast. And secondly, they are truly bidirectional, okay. They are truly bidirectional. So that is the advantage of going for transformers. So when you say truly bidirectional, so if the use case, like you want to convert from English to French or French to English, the transformers, they have two things in them. Transformers, they have two things. They have encoders and decoders, two networks, okay. So what does encoders do? Encoders, they take enough English words simultaneously and creates embeddings, okay. That's what encoders do. Take the words and create embedding simultaneously, okay. I mean both happens parallelly, takes the words simultaneously and creates embedding simultaneously. So what are they? Um, they are embeddings, that is vector spaces, vectors that encapsulate the meaning of the word. So what are vectors basically? If you already known what are vectors, in they are similar words. I mean closure vectors are similar type of words. If I say is and are, might not be same words, but they are closure vectors, I can say, because they may be related to same context. If I say Prime Minister and Narendra Modi, they may be different words, but still they are connected to same. They may have near vectors because Narendra Modi is the prime minister. Okay, so similar words have near vectors. Okay, so that's what encoders do. They form vectors by understanding the embeddings. And secondly, the transformers have second part was decoders. So decoders, they take the embeddings from the encoders and then generate words of the translated French or Italian, whatever sentences, and it tries to spread the next word. Okay, takes embeddings from encoders and creates the translated words, or generates the next prediction. Okay, so it has separation in these tasks. Firstly, so transformers, they have two tasks: encoders and decoders. So encoders, so the main part of encoders is just not to do this embeddings. What it is doing in embeddings actually is it is trying to understand what is English, what is grammar, what is context. So that is what is happening. The understanding part is happening in encoders. And decoders, they try to map these words to the translated words. Suppose if I'm doing neural translation, so it is trying to map English to French. So encoders, what they do, they just try to understand the embedding or the language or the grammar and the context. And decoders, they just try to map the English words with French words, or they just try to do the next predictions, the mapping predictions. Okay, and they both are underlying understanding of the language. Okay, both are required for a neural machine translation type of subject. You require both the understanding of the language. Even if a person, you need to understand and you need to map it. The same thing happens in transformers. So they try to understand the language and they try to map the language. Okay, so both are underlying concepts of the language. Okay, so that is what is the main functionality of transformers. Okay, which is not actually happening in any other networks. That is where the context has been recognized properly in transformers type of understanding. Okay, we haven't come to BERT yet. It is just any transformer I'm speaking about. Okay, so in this, if I say the transformers, there are two parts, right? Encoders and decoders. So encoders, I can say example is BERT. Decoders, I can something like GPT or something. Okay, maybe decoder you can say as GPT or something, but I'm example of encoder is BERT. So BERT is what? It's an encoder. So BERT is an encoder, and encoder part of transformers, if I say, or anything. So BERT is an encoder. Okay, and decoder can be example of GPT something. Currently we're discussing on encoders or BERT. So here the word embeddings of BERT are little different, how they are trained. Okay, so the use cases, if I say, with respect to these are many neural machine translations. Let me sum them up. Neural machine translations. Q&A. Q&A is what question answering system. So there's a good popular use case like question answering data set. So you just ask a question to a data set, it will give the answer, like a passage comprehension, question answers. Okay, Q&A, sentiment analysis, the proper way, text summarization. See, for all these things, use cases, you understand the main part is understanding the language. That's why BERT comes into picture very good with this, because obviously any word embedding works, but BERT has more capacity because its embedding is a little more prominent in understanding the context. So for neural machine translation or Q&A or sentiment analysis, text summarization, one part is the main thing, that you need to have good understanding of context of the language. So that is very much good with BERT, and that is very much good with transformers. So that's why these use cases have better popularity than any other. Okay, so how does BERT work now? Yeah, so how does BERT work now? So first, there are two things on how BERT works. Firstly, the first part is pre-train, where there is called pre-training BERT to understand the language, and second thing is fine-tuning BERT to learn specific tasks. Okay, I hope this was clear. So firstly, pre-training BERT to understand language, that is embedding only in one way, and secondly, fine tune BERT embedding, or fine tuning BERT to learn specific task. Okay, fine tuning BERT to learn specific task. I'll explain this. So obviously, pre-training and fine-tuning. So what is pre-training? So basically the first pass, So in pre-training, it is doing embedding and trying to understand what is language, what is context, as I was saying previously. So it does pre-training, but the thing is, BERT does pre-training in two supervised tasks simultaneously. Okay. So firstly, it does pre-training in two unsupervised tasks simultaneously. Both supervised and unsupervised tasks happen simultaneously. So what are those two tasks? One is MLM. What is MLM? Mass language modeling. And secondly, NSP, next sentence prediction. Okay, so it happens in two ways, MLM and NSP. So what is MLM? Mass language modeling. So what is mass language modeling, if I say again? So it is like fill in the blanks type of scenario. So what it does, it is trying to learn by masking some of by some of the words. Suppose if I take an example, suppose if I take an example, like a quick brown fox like runs over jumped over a lazy dog. I think the popular sentence. I'll show it. So MLM example, suppose. So if we say Yeah. So what it does is MLM. So the mask one brown fox, mask two over a lazy dog. So it is trying to predict the fill in the blanks. So the answer would be mask one is the quick brown fox jumped over a lazy dog. So it is trying to mask some of the words and trying to predict it. Okay. So goal is to output the masked words. Okay. MLM goal is to output the masked words. Okay. Okay, so that is how it's like fill in the blanks, as I said, learning in your school, you learn things by fill in the blanks, right? Similar way, MLM is trying to learn by fill in the blanks. Okay. Secondly, NSP. So NSP is what? Next sentence prediction. So here it takes into consideration like two sentences and checks if second sentences follow the first sentence. Suppose I give an example again here. So sentence one. Mr. Modi is great person. Okay. Mr. Modi is the PM of India, Prime Minister of India, and lives in Delhi. Okay, so these are the two sentences. It is trying to check in the next sentence prediction. It is trying to check, if the second sentence follows the first sentence or not. Yes or no. Okay, so it is trying to select the next sentence prediction and trying to predict kind of yes or no if second sentence follows the first sentence or not. Okay, so to summarize till here, firstly we discussed on what is the issue with LSTM, and then what are transformers, what are the advantages of transformers of LSTM, and what are transformers. They have encoders and decoders. So if I say decoders, they create embeddings simultaneously, and decoders, they take the embeddings and do the specific next generation predictions or next predictions. And if I consider example of encoder is BERT, and example of decoder as GPT or something, but now we are discussing on BERT. So BERT is an encoder and it can be used in transformers as an encoder. So what are the use cases? Neural machine translation, Q&A, sentiment analysis, text summarization, where the context is very important of the language. So how does BERT work? Yeah, there are two ways. One is pre-training and there are not two ways. There are two things. First, one by one. So firstly, it does pre-training, and secondly, it does fine-tuning on specific tasks. So pre-training, how does it do again? It does on two methods. One is MLM and NSP. MLM is what? Mask language modeling. So mask language modeling. So it is like a fill in the blank scenario where it is trying to mask certain words and trying to predict it. And NSP, next sentence prediction, it is trying to check if second sentence follows the first sentence or not. So that is how till now we have discussed the summarization. So we have discussed now pre-training, and now we need to discuss on what is fine-tuning in BERT. BERT works in two ways: pre-training and fine-tuning. Pre-training is done, now fine-tuning. Yeah, so fine-tuning, how does it do? Is a pass-through basically. So how to how to use layers in a specific context, that is important. Okay, so fine-tuning. So if I say example like Q&A, I was saying, right, the question answer scenario. So where there are a lot of question answers or paragraphs where you ask a question to BERT and give a paragraph, it will say the answer. Okay, it's like in childhood you have learned, right, the question answer of passages and comprehensions, right? So here, technically speaking, it replaces a fully connected layer of the fully connected output layer with the first set of output layers, and then the output of question answers are fed. Okay, so we already have a pre-training. So fine-tuning, how it does? It is trying to replace a fully connected layer and give the input with respect to the question answer dataset. So it is like question and passage and BERT, and it will give the answer, like question and answer, and you give to the BERT and gives the answer. Obviously that is a method. So things happen simultaneously, that's all. So not question answer, question and passage. Okay, yeah, question and passage happen simultaneously, and it goes to BERT model and gives the answer. So how does it do the fine tuning? Already the fully connected layer is already there, so it is trying to replace fully connected layer, basically connected output layer, with first set of output layer and feed question answer dataset. Okay, so it's like summing up here. So it performs supervised learning with question answer dataset. That's what I can say. Okay, it performs supervised learning with question answer dataset. So previously it was still unsupervised. So it performs supervised learning with Q&A dataset or something. Any dataset basically. Okay, so it thing is, the advantage is it won't take too long. It won't take too long. Why don't wait too long to train? It won't take too long to train. So it won't take too long to train because already pre-training was done, the parameters are already there, so we just need to slightly fine tune. Okay, only fine tuning is required. Already all the parameters are already trained, only we need to fine tune on the end output parameters, that's all. It won't take too long in training using BERT with any specific task, because already the parameters are trained, and we just need to slightly modify the output parameters for our specific task. Okay, so that's why I was saying 90% job is done with BERT, only 10% has to be done. That's why it is very fast. Right, so training time is very fast, so it can work with any NLP task. Just replace output parameters and your training dataset is done. Okay, right. So to go a little more in detail about the BERT understanding, I can say, let me show the BERT firstly how the BERT looks. This is the BERT attention mechanism. So this is like, I like cats more than dogs, and this is the translation Chinese, I hope so, and then Chinese. Okay, so bidirectionally it is trying to understand the encoder transformer mechanism. Okay, it is trying to get the word embeddings and then trying to work on the specific task. So if I say overview in the broad view, how it is like this, just the encoders, technically speaking, just the encoders. Okay, so now the main part of BERT. So there are a lot of layers on working with BERT. So firstly, the input layer. So as you see, the structure, the architecture of BERT is like this. So it has input layer firstly. So input layer, it's simply a vector of sequence tokens along with special tokens, like written here. If you see the CLS, my dog is cute, SCP, he likes playing. Okay, so they are just simply a vector of sequence tokens with special tokens, like ing is a special token. So what is /ing? In BERT uses word piece. There's something called word piece, not world piece. Okay, so it's word piece. BERT use word piece for tokenization, so which splits the playing as play and ing. So the advantage of using this special type of tokens is it covers it covers wide spectrum of out of vocabulary words. Okay, so here it uses word piece type of tokenization to and splits this ing and these type of words and tries to cover wide spectrum of out of vocabulary words. So it's simply a vector of sequence tokens. That's all. Input layer. Okay, and it is trying to mask, as I said, mask dog, mask likes. So it is trying to mask. And secondly, token embeddings. The second layer is so token embedding is simple. Basically, it is just the vocabulary IDs for each of the tokens. It is just trying to capture the vocabulary ID to remember in future. Use in future. Okay, and thirdly, sentence embeddings. It is just a numeric class for distinguishing between A and B. Okay, the first and second sentence. Okay, so sentence A is my dog is cute. Sentence B is he likes playing. Okay, so sentence embedding, it is just trying to it's a numeric class. It is trying to convert as a numeric class and distinguishes between the sentence A and B, and just checking whether A follows B or B follows A or not. Okay, as I said previously, what BERT does, MLM and NSP, so we only train these two in the embedding structure. So masking, that is very input layer, and token understanding, token embeddings, and sentence embeddings. Here it is just tokenizing the sentences. Okay, the numeric class. And thirdly, the transformer positional embedding, which is the important layer of BERT, which is special layer, but the main part of transformer positional embedding is token embedding and sentence embeddings are common, but transformer positional embedding is something which is part here. It indicates whether the position of each word in the sequence is right or not. Okay, so it is just trying to help you out in positioning. Okay, so whether the word is following properly or not. Next word prediction is happening based on this understanding only. Okay, to summarize this, the input layer, so it is simply a vector of sequence tokens, and it has special tokens like ing, and it uses the word piece to tokenize the BERT. And second, token embedding, so it is just capturing the vocab IDs. And sentence embedding, so it is just a numeric class for distinguishing between sentence 1, sentence B, sentence A and B. Okay, and lastly, positional embedding, transform positional embedding, so it is so simple that it tries to indicate the position of the word in the sequence. Okay, and in detail, if you see, the BERT layers are such complex. It has 12 layers, 12 layers in between, right? So this is structure of BERT layers, and that's how BERT works. It is so complex, but if you understand it in this methodology, it is so simple. Just two parts. One is pre-training and fine-tuning. Pre-training has MLM and NSP, masking and next sentence prediction, and fine-tuning is as per your parameters, the output parameters have to be modified for the specific task. That's all. And the advantage is it's a transformer, it is trained on a lot of data, so the embeddings will be a lot more perfect, and the context is maintained for every word. So if I say apple, it will change the context will change of the word apple. The word embedding value of the word apple will change according to sentence. See, in normal word to vec, if you heard of word to vec or glove word to vec or normal LSTM or any word embeddings, if you see the every word apple, if I say, it will have some vector assigned. It is fixed. if you say apple vector versus apple vector, it will say the distance between these two vectors is 0 because both are same. But in BERT, if I say the distance between the word apple and apple, it will be different because it depends on the context. I'll say an example. So if I say a normal word embedding, or word to vec scenario. So if there are two words, I love eating apple, or apple has released new iPhone. So in these two sentences, if you see, both have different context in this. Okay, so here apple has different understanding, here apple has different understanding. Here apple is a fruit, and here apple is a company. Okay, so both are different. But if you say in word to vec, if you say the distance between apple comma apple, it will say distance is 0 of the vectors. The vector might be something like 0 1 or something like any vector. So vector might be anything, it can be some random vector. So but the distance between these two vectors is 0 because both are same. But in case of BERT, it's the same thing, but if you say the distance between apple and apple, it will have difference. If you project in a word space, okay, it will say something like 20 or 30 similarity distance or something. Okay, so thing is, the distance is varying, all the words are same, it is varying because BERT understand the context of single word with respect to multiple sentences, but word embeddings, they don't understand the context with respect to word, they understand the context with respect to same word, they understand the context with respect to different words. Suppose if I say distance between apple and orange, it will say properly, it has understood the context, apple is a fruit and orange is a fruit, so they might be near vectors. Okay, so that understanding has been done by word embedding. Okay, if I say apple and comma orange, it will say the vectors are same because both are fruits, not same, nearly same, maybe 1-2 differences because both are same type of category. But but if I say apple and apple, it will not work. Okay, but in BERT, with respect to same words, it will have different understanding. So that is an advantage. Here the context is little more deeper compared to word embeddings. Okay, I hope this was clear. What is a word embedding and what is the context, and what is a word and what is its context. I hope this was clear. Yeah, I'll explain the context of this context of embedding with respect to word to vec and BERT separately now. Okay, so I just took a Colab notebook, Colab, so because this has GPU and all, it's faster speed, so it will not work in my system, so I just took Google Colab. You can use it if you want also in your systems. So I took Google Colab. So I'll explain the contextual embedding difference between word to vec and BERT embedding difference. That is the thing I want to show you now here. Word to vec versus BERT embedding difference. See, only thing that differs is context. Okay, so I have already installed Flare for now, because Flare is a good NLP package and can work with multiple word embeddings. So this is quite comfortable for now for you to understand this. I'll import all the embeddings required. So one is I have imported word embeddings which has glove, and transfer embedding which has BERT. Okay, in the sentence which will work with two sentences, I will show that, and the distance between the vectors of two words, I can show that context. Okay, so now if I say I'll take glove embedding. and I'll take BERT also. I think it's downloading. Glove is downloading now. So BERT embedding is BERT space, sorry, dash. Yeah. So glove is done. Now BERT, I'll be downloading the word to vector. So we have two word embedding vectors we downloaded: glove, word to vec, and BERT embedding. So glove is generic, we already know, existing one. BERT is a new one, transformer embedding. So we have BERT loaded and glove loaded now. So I'll have now two sentences. Sentence 1 equal to, suppose I'll take the example of Apple itself. Sentence of new iPhone 12 Pro has been released by Apple recently. And sentence 2, eating an apple is healthy and good for health. Sorry. Okay, I took two sentences. So if you see, so here the word apple has different meaning. Here the word apple has different meaning. It's here it's an no fruit. Here it's an organization. Okay. So I've just taken two sentences. So let me check the embedding of sentence 1 and sentence 2 now. Okay. We have embedded it. So sentence 1 of the word apple -1 -2, right? Yeah, it's apple there. So what is embedding now? Cent underscore 1 of -2 dot embedding. Yeah, this is my embedding for glove, and let me check the shape. The shape is 100. Okay, so it's using torch. So same thing I'll do for sentence 2 also. For token in sentence 2, suppose I'll just take for all print token parent token not embedding. Yeah, so here sentence 2, apple is this one, right? So even let me check the shape for it. So it is what? 0 1 2 3 sentence underscore 2 of it's apple. So let me check the embedding shape. The shape is 100. So now we have two sentences. In the sentence 1, apple is different, the sentence 2, apple is different. See, if I just print if you see here in this both sentences, the sentence 1, I'll print that also. I'm trying to explain what actually it is. Yeah, so if I see, the first sentence is eating an apple daily is good for health, and second sentence is new iPhone 12 Pro has been released by Apple recently. So if I just check these two embeddings and I only take the tensor apple token, tensor apple, so the tensor embedding for apple is same, 0.6686, 0.3490, 0.6686, 0.3490. So this glove and word embedding, what it has done, it has taken apple as one single context word and created a same vector. But if you see the sentence, here apple is not an organization and here apple is not a fruit, but the vector, the understanding as per glove is same. It has taken apple as one single word, one single context, one single vector. But actually these two should be actually different vectors, because both are in different. The spelling might be same, the word might be same, but the context is different. If I say this sentence to you, you obviously understand apple is not a fruit here. If I say this sentence to you, will obviously understand, your mind will understand automatically that apple is not a organization here, it's a fruit here, right? The same thing is not happening with this vector, with this embedding, glove embedding, right? So this is the problem in using word to vec with words like this. If I say the word different, the word embedding between apple and orange, it will say maybe, yeah, then they are nearer words, both are fruits, maybe. But if you take example of apple and apple, the distance between them is 0, because both are same vectors. Let me show that also. If we have scipy imported, so if I just say suppose glove distance, so if you check the distance now, distance between these two was 0, obviously, because both are same vectors. So that is the problem with using word to vec. Even though same spelling, same word has different meanings, but the vector is same, the context is same, the distance between the two words obviously 0 because the vector is same, both are same vectors, but actually they are not same. Apple and apple are same here, but not actually same. Spelling is same, but the meaning is different. Okay, this issue, the contextual understanding, is solved using BERT. Contextual understanding is solved using BERT. BERT can understand what is apple in different sentences. Basically, it creates different vectors, different word embeddings for same words according to the context. This is a perfect definition of BERT. Okay, BERT, it creates different vectors or word embeddings for same words with respect to the context. You can just write it as definition itself. It creates different vectors or word embeddings for same words with respect to context. Okay, now I'll do BERT embedding. Okay, so we already have BERT embedding. I'll just again run it for safety. Yeah, BERT is already there. So we already have sentence 1, we already have sentence 2. Yeah, sentence 1 and sentence 2 both are there. So now what I'll apply BERT embedding. Okay, and let me check the embedding now. Sentence 1 dot embedding. So it's empty. Sorry, sentence, we can't do embedding for this, right? Sentence for a word we can do, right? Sorry, sentence word of -2. Let me check that. It's apple dot embedding. Yeah, we got a tensor like this. Let me do the same thing for sentence 2 also. And sentence 2 of 2 is what apple again, right? Yeah. Now again I'll check the sentence embedding here. Apple embedding basically here. Yeah, if we check this sentence 2 embedding and sentence 1 embedding, what is the difference? Both are different. -5985, -4632, 01300, and it has changed. 0.8390, 1.6440, 0.3022, -1.1050, 2021, 2334. So the embedding of apple is different here. Okay, I'll just show it clearly, the difference. As before, no, I already have it here. Right. yeah, it's clear now. Sentence 1, the word is token apple and the tensor is here, token 2 apple, the tensor is here, 2021 2324. Both are different. In the previous case, if you have seen, both are same, both are exactly same. Okay, and if suppose I check the difference or the BERT distance, suppose I write it BERT distance, sentence 2 of -2, the embedding has changed, right? So the distance between apple and apple is 47.57, but if you check in glove, distance is 0, but the distance between here is 47. So BERT has actually understood the context here. That's why when I asked the difference between the word apple in the first sentence and the word apple in second sentence, it has understood both are not different, both are not same words, both are different words. Those should have different word embedding, they should have different vectors, so both are different. So it has created two different vectors for the same single word apple and created contexts for it. So that is the advantage of using BERT. It perfectly understands the context of a single word. Okay, even the spelling is same, it can create multiple vectors, multiple embeddings for the same. That is the advantage of using BERT. Okay, if you want to just summarize, I can say the same understanding, the definition. It creates different vectors or word embeddings for same words with respect to the context. That is the advantage of using BERT over any other word embedding or any other glove. So BERT can understand multiple vectors. Thanks guys. Try to experiment with BERT. You will have a good advantage in your applications. Any use case, let me know.